Hi everyone, welcome back. So last time we talked about those electrons, those ones that were like the orbital that was so close to being filled or to being empty, which would have made us have a nice full shell. Because electrons, I mean, the shells don't look literally like this, but they hate being partially filled. They would rather be completely empty or be completely filled, not one or not in between. So that those electrons, that's where those atoms, are going to do whatever they can to fill in that shell or to empty it. So if it's mostly empty, they're probably going to get rid of that shell. They're going to get rid of those electrons so it can be empty. If it's mostly full, they're going to try to fill it in. Now, where these shells come from, the number of electrons that they want to lose or to add, they all comes from the quantum numbers. Remember, we start with shell 1. Shell 1. And I'm going to go ahead and let's erase some stuff here. And so in shell 1, that's equals n, L can equal 0. So this does not mean there's no orbitals or no shells, it just means that's our only number. That's a quantum number. It's like an address, okay? It's the 0th house. It's kind of weird. Then ML can go from negative L to positive L. And since it's 0, well, there's negative 0 and positive 0 the same thing, so that's only 1. So 1 orbital. And so in the first shell, we can only have, let's go say MS, 2 electrons. One would spin up, one would spin down. And so that's why we see 1s2. For L equals 0, well, that is the S shell, S subshell. The 1 right there is referring to N. It is the shell. So we have a shell, we have a subshell. Now, as soon as we fill up one shell, we begin filling the next one. And that's what you see right here. So this is the second shell, and then these are the subshells. And you can see from here, okay, well, 2s2, we see our S subshell. This is an S subshell, and all of our S subshells can only have 2 electrons. And we have this P subshell, and you're like, well, what's that? Well, let's see if we can find that P shell. You probably remember it from last time. We'll go over it one time, then we're going to keep on heading on. Okay, so for n equals 1, well, L is still going to be equal to 0. It's always, sorry, n equals 2, my bad. It's going to be either 0 or 1. You already know that L equals 0, that's S. So let's try 1 out and see if that gives us something different. Well, ML is going to be able to go from negative L to positive L, so negative 1. Then I add 1, so I'm at 0. I add 1 again, I'm at positive 1, so I stop. Positive 1, negative 1. And then each of those is going to be able to have 2 electrons in it. Negative 1 half, 1 half. Negative 1 half, 1 half. Negative 1 half, 1 half. Okay, so this second type of subshell, it can hold a grand total of 6 electrons. So that would probably be the P subshell. So L equals 1. Sorry, that away. L equals 1 is going to be the P subshell. And it can hold 6 electrons. But you see there's an issue here. 2p2. It wants a full shell, not just a full subshell, everybody, a full shell. It's going to do anything it can to get rid of these electrons or to gain more electrons. So if we look at it, to fill in this orbital, this subshell, it has 2, so we're good there, but we need 4 more. So this guy wants 4 more electrons. Okay, so those are electrons we're trying to grab. Now, these electrons right here, these are my valence electrons. They're in their outer unfilled shells, okay? The filled shells are much more stable. These aren't going to do anything. This one, it's like it doesn't even exist. Nothing can see it because there's so many other electrons that are outside of it. The valence electrons, though, are available for bonding, and they tend to determine an atom's chemical properties. Those are the valence electrons. Okay, so let's look at this again, but now with a much bigger graph. We're going to start filling in all these shells. So this is for iron here, okay? Iron has a whole bunch of electrons. It's got 26 of them, to be exact. So first off, we start in our first shell. This is the first shell right here. 1, 2, 3, 4. And you see there's kind of a weirdness here, like, wait a second, isn't that the third shell? Yes, it is the third shell, but technically for quantum mechanics reasons, this one's lower in energy, so it happens first. I know it's weird, it's kind of a strange thing, but don't worry about that too much. There's never going to be a question where you get that wrong because that's the case. Okay, and so we start filling in all 26. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 so far, and then we start filling them in. As a note, you always put 1 electron in each orbital before you start putting 2 in an orbital. Okay, so you see right here we got 4 left to fill in that orbital. Okay, there's 4 left, and so this guy has 4 more electrons that it would like to grab to be nice and happy. Now these guys right here, those are my valence electrons. You might be wondering, like, well, how come that's the 4th shell? Aren't we worrying about this? It's all because of energy. This is neither part of the full 4 shell, and this 3rd shell is also not full. Since these p subshells are full, they're much less likely to react. So when you fill in a subshell, it typically is happy as well. It's not completely happy, but it's more happy. These would be our valence electrons here. So you see it has 8 electrons to bond with, which is why iron bonds with everything around it. Okay, so that is it for this time. Just remember those electrons on the very end from those unfilled orbitals. Okay, those unfilled orbitals or unfilled shells. This one right here is in an unfilled shell. This one's from an unfilled subshell, and they become our valence electrons. Another little detail, why are they the most reactive? They're the most reactive because they're on top. They are the highest in energy. High energy means that they want to pop off, and they do that very easily. Okay, so with that, we'll end it here, and next time we'll actually begin going into the different types of bonds, at least building up into that. So I hope this helps you, and I'll see you all next time. Bye-bye.